Hello everyone, I'm Xingyao Zhang, a postdoc scholar from Bespoke Silicon Group of University of Washington. Welcome to our talk on highly efficient LargeLSTM training. And we're using the memory saving and architecture design opportunities. This work is a collaborative work between the University of Houston, University of Washington, and University of Sydney. I-LSTM stands for the Long Short-Term Memory Networks. This is one of the most popular type of the recurrent neural network. And this recurrent neural network has been widely applied into the real-world applications. For example, the figure we showed here. So we can see that the LSTM actually become more and more important. The use cases are increasing and the data scale also grows, which eventually makes the LSTM model become larger and larger. And these large LSTM models become complex and hard to train for both the real-time on-device training or offline training. Let's take a look at how the state-of-the-art training for an LSTM layer is conducted. The LSTM layer should first perform the forward execution, which takes the input to generate the output. Unlike a CNN, it also needs a historical output as another input to pass the context information back. Generally, an LSTM forward layer can be unrolled into a sequence of the cell. And each cell takes only partial inputs and context to produce partial outputs. The cell computation are shown in the zoom-in figure here. This computation can be grouped into two executional kernels. One is the general matrix multiplication or GEM. Another is the element-wise operations. Similarly, the LSTM backpropagation processing can also be unrolled, and it takes exactly the reverse computational direction. The computation of a BP cell can also be grouped into a GEM kernel and an element-wise kernel. When the LSTM model becomes large, what will happen for training, performance, and energy? To get the sense of this, we test the throughput and energy efficiency for LSTM training when the model becomes larger and larger. There are three ways to increase the model size, either by increasing the hidden size, or layer numbers, or layer length, which is the number of cells in one layer. The test was conducted on the latest GPU, NVIDIA V100 and RTX 5000. We have the high level observation that the performance and energy efficiency significantly decreases when increased the model size. Also, we find that the training becomes increasingly infeasible to be conducted on a single GPU. Finally, we find that the state-of-the-art training solutions doesn't scale with the increasing LSTM model size. To figure out why the large LSTM training becomes inefficient, we first perform the detailed calculations on the LSTM execution. We discovered that the element-wise computation produced a large amount of the intermediate variables. When only performed inference, we don't have to care about this. But when it comes to the training, these intermediate variables will need to be stored and loaded back for backpropagation. So previous work has some recomputation strategies to reduce the data movement for CNNs or transformers, which is basically store only the partial data and recompute to get all of them during the backpropagation. But for LSTM, the computation towards this data are too much. And basically you need to recalculate nearly all the forward computations to get this data. To quantify the impact of the intermediate variables, we evaluate both the data movement and the memory footprint breakdown for different LSTM models. We observe that much more significant data movements are caused by the intermediate variables than both the parameters and the activations. Also, we find that these intermediate variables takes a major part of the total memory footprint. It's nearly the half. So, in order to address the inefficient LSTM training, we first have two optimizations from our software level design. We propose to reduce the intermediate variables at the cell level, as well as reduce the backpropagation layer length to reduce the data movement. For cell level reduction of the intermediate variables, based on our two major observations that some backpropagation computation can be rescheduled to the forward stage, and its output is sparser. So we're able to redesign the LSTM execution flow to replace the intermediate variables need to be stored with a sparser one, so that a more efficient LargeLSTM training can be enabled. For BP length reduction, another way to reduce the LSTM model size, we have an important finding that some BP cells offer insignificant contribution to the weight update. And we leverage this fact to design a BP layer length reduction scheme. We will introduce these details in a little bit. In addition to the software level design, we propose a new hardware design that complements these software optimizations, and it further improves the LSTM training efficiency as follows. At a lower level, we introduce the OmniP design that the logic will be reused for different functionalities that help achieve a high logic utilization. This will eventually benefit the hardware throughput and energy efficiency. At the high level, our η-LSTM architecture can pipeline the two kernels' execution, and the computation resource is dynamically scheduled, so it won't be idle logic and harm the overall performance. The control overhead is quite small because the execution pattern is kind of fixed. With the gem and element-wise kernel pipelined, massive intermediate data between these two kernels can be quickly consumed. And our design achieves amazing good results on the FPGA. We implement our accelerators on the Xilinx VCU128 FPGA board and show that even in the FPGA emulation, we beat the state-of-the-art NVIDIA V100 by on average 4 times in performance and by on average 2.75 times in the energy efficiency. This is the outline of my talk. I have finished the introduction and motivation. Next, I'm going to discuss our software and then hardware design strategies and optimizations. Following that, I will demonstrate the key evaluation result and then conclude my talk. So for software optimizations, we have the key observation on the intermediate data. That we find the intermediate data between the forward cell and the backpropagation cell is dense. And that gives us a very small opportunity to reduce them. But we find some backpropagation computation only requires the data from the forward cell, which means that this part can actually moving forward to the forward stage. And this part actually generates much sparser data compared with the forward element-wise output. This figure shows the sparsity difference between the forward computation results, which are the original intermediate variables, and the results from those partial backpropagation computations. The upper two lines are the value distributions for the output of that partial backpropagation computation, and the lower two lines represent the data distributions of the vanilla intermediate variables between the forward and backpropagation procedure. As we can see from the figure, when the threshold is small, there is around like 50% sparsity difference. So the BP's computation actually provide a much better opportunity for us to compress the data movement between the forward computations and backpropagation computations. Therefore, we propose our cell level reduction, which contains moving forward those partial backpropagation executions that requires only the forward variables, applying the zero pruning compression on these executions and saves both value and index into the DRAM. Finally, since the input data becomes sparse, the partial computation of the remaining backpropagation processing can also be skipped using the index information. In summary, with reordering, not only the data get compressed, but also the computation get reduced. Both are good for performance and energy of the LSTM training. In addition to the cell level reduction, we propose to reduce the BP layer length as well. We have another key observation that the contributions to the cell computation is different across the cells. In other words, there are some cells are more important than the others. The importance is evaluated by the weight gradients distribution, because all the BP cells in the same layer contribute to update the same weight matrices. The left and right line figure demonstrate the weight gradients magnitude changes for different cells at the same LSTM layer. A trend is either decreasing or increasing. It's all related to how loss is calculated and passed. But just superficially looking at the figure, some cells contribute nearly nothing to the weight update, like the cell number 60 to 0 in the single loss one, and the number 80 to 50 in the per timestamp loss case. Since we find some cells are trivial, we can identify them and skip them. In order to identify those trivial cells, we build a mathematical model, which takes the LSTM layer config and final loss into consideration. With this model, we can set a threshold to determine whether the cell is significant or not. So this is diagram for BP cell skipping. We only need the weight gradient from the significant BP cells, and we further scale the partial result to get the gradients result for the entire LSTM layer. Next, we further propose several hardware level design and optimizations. The hardware design should be sticked with computation. Based on our previous discussion, the computation of the forward cell and backpropagation cell can be divided into gem and element-wise kernels. However, these two kernels perform different computations. Note that the accumulator and the adder are actually different in terms of the logic design. Besides, these two kernels have different workload, which is gem much larger than the element-wise. So the problem is that if we put these two kernels into a separate module, which is actually popular for LSTM inference accelerator design, the module for the element-wise kernel will be in idle for the most of the time. But if we conduct a naive design to put all things into the same PE set, then this PE design will be too complicated, and a lot of logic still in idle, and design area is also large. Besides, such design requires one kernel finished before another kernel is executed, just like GPU. So the intermediate data between these two kernels may need to be stored into the DRAM, which causes the large data movement overhead. So we're trying to address this challenge, and we choose the angle of trying to reuse the logic for adder and accumulator so that the logic utilization could be improved and the PE can become more flexible to serve different executions. The problem is that the adder has latency to produce results, so if we perform A plus B plus C, we actually need to wait for A plus B's results, then conduct the calculation of plus C. So we solve this problem by appending a buffer or queue after the adder, and control the execution flow to form the stream processing of the accumulation, just like the way illustrated in the table. With the logic reused between the adder and accumulator, we have our OmniP design, which enables all the LSTM training executions except for the activation functions. And it has a pretty low area overhead and potentially high logic utilization, so the design efficiency is quite high. We have channels to hold multiple PEs and the activation modules. And channel is exactly the level to switch the functionality to serve the different kernels. This is our entire accelerator architecture. And specifically, we have customized the controller to enable the dynamic channel functions wing. So different channel could perform different kernel based on the demand. All the computation resource can be leveraged, and then the intermediate data can be fast consumed as well. We also customized our DMA to support the computation skipping from our software optimizations. I have talked about our optimizations. It's time to show how effective they are. We use the latest GPU to conduct the baseline case and the pure software implementation. Our hardware design was performed on the Xilinx VCU128 FPGA board, and we evaluated 6 most popular LSTM benchmarks. This figure shows the effectiveness of our optimizations on the LSTM training. And we observed that our software optimization can achieve on average 1.56 times and up to 1.79 times speed up on the GPU. And our hardware design achieves on average 1.42 times and up to 1.85 times speed up compared with the baseline GPU. And combine them, we can actually achieve on average 3.99 times and up to 5.73 times speed up compared with the baseline case. And our optimizations also achieve great improvement for energy. And our software optimizations achieve on average more than 1.5 times speed up on the energy saving. And our hardware optimizations achieves more than 1.6 times on the energy saving. Together, our i-LSTM achieves nearly 3 times on average for the energy saving, and this number could as high as more than 4 times in some case. This 3 figures shows that our i-LSTM can effectively reduce the data movement for weights, activations, and intermediate variables. For example, here the weights is reduced on average 20%, and it reduced on average 30% on the activations, and it also reduced a lot of the intermediate variables data movement by 80%. We further evaluate the i-LSTM impact on the memory footprint. As shown in the figure, the activation data and the intermediate variables get reduced a lot. There are many works focusing on the neural network acceleration, but most of them are for CN or LSTM in inference. Since LSTM training is very different from CN or its inference, the solution can hardly address our problem. There are also memory footprint reduction works. They propose the weight matrix recompression and recomputation scheme. But memory footprint problem of the LSTM training comes from the intermediate variables, and the compressive weight can hardly reduce the intermediate variables amount. On the other hand, it is costly to recompute these intermediate variables for the LSTM training, as we discussed previously. So making the recomputation scheme not an appropriate solution for the LSTM training acceleration. And our work here is the first work to accelerate the large LSTM training, and we leverage the unique LSTM training features to reduce the memory footprint and data movement. To conclude my talk, we conduct a comprehensive calculation study for large LSTM training on the state-of-the-art architecture and identify its root causes for training inefficiencies. At software level, we introduce several key observations regarding the unique LSTM training data pattern, which are then leveraged to enable the large reduction on the memory footprint, data movement, and training latency. At hardware level, we propose a novel architecture design to enable the high logic utilizations on the customized NPUs, while supporting our software level optimizations and further enhancing the LSTM training performance and energy efficiency. So our proposed i-LSTM outperformed the baseline case GPU by on average nearly 4 times on performance and nearly 3 times on the energy consumption. Even these results are emulated on the FPGA. Thank you so much for attending my talk.